Hello everyone, and welcome back. In our last session, we explored the concept of the derivative graphically, understanding it as the gradient of a function's tangent line. Today, we're going to move from sketching to calculating. Our main goals for this lesson are twofold. First, you will be able to find an exact algebraic expression for the derivative of many common functions. Second, you will be able to use that derivative to analyze the function's behavior, specifically to find the intervals where it is increasing or decreasing. Let's start with a quick recap to bridge the gap between the graphical and the algebraic. Remember the key relationship. The value of the derivative function, f prime of x, at any point tells us the gradient of the original function, f of x, at that same point. So, the derivative function's value is the original function's gradient. Consider this function, f of x. It's a downward opening parabola. Let's think about its gradient. On the left side, as we move from left to right, the function is rising, so the gradient is positive. Notice these tangent lines. They all have a positive slope. At the very top, at the vertex, the tangent line is horizontal. This is a stationary point, and its gradient is 0. On the right side, the function is falling, so the gradient is negative. Here, the tangent lines all have a negative slope. So what would the graph of the derivative f prime of x look like? It needs to be positive, then 0, then negative. It would be a straight line that starts above the x-axis, crosses the x-axis exactly where the original function had its stationary point, and then goes below the x-axis. The derivative of a quadratic is a linear function. This graphical method is great for intuition, but it's not precise. Today, we'll learn how to find the exact equation for that derivative line. This brings us to our first major tool for differentiation. We are now finding an expression for the derivative. There's a simple, powerful rule for differentiating functions of the form f of x equals x to the power of n. It's often called the power rule. The rule states that if f of x equals x to the power of n, then its derivative, f prime of x, is n times x to the power of n minus 1. Let's break that down. There are two steps. You bring the original power, n, down to the front as a multiplier. Then, you create a new power by subtracting 1 from the original power. Let me repeat that. Bring the power to the front, and reduce the power by 1. Let's see this in action. Suppose we have the function f of x equals x cubed. Here, our n is 3. So we bring the 3 to the front, and the new power will be 3 minus 1, which is 2. So the derivative is 3 times x to the power of 3 minus 1, which simplifies to 3x squared. It's that straightforward. Let's try another one, this time with a negative exponent. Be careful with your arithmetic here. Let's find the derivative of y equals x to the power of negative 4. Our n is negative 4. We bring minus 4 to the front. The new power is negative 4 minus 1, which is negative 5. So dy by dx is equal to negative 4 times x to the power of negative 4 minus 1, which gives us negative 4x to the negative 5. A common mistake is to say the new power is minus 3, so be careful when subtracting 1 from a negative number. Okay, but what if there's already a number in front of the x term? For example, what about something like 2t to the power of 5? This leads to our next rule, the constant multiple rule. If a function is of the form a times x to the n, where a is a constant, its derivative is simply a times the derivative of x to the n. In other words, the constant multiplier just tags along for the ride. You differentiate the x to the n part just like we did before, and then you multiply the result by the constant a. The constant is unaffected by the differentiation itself, it just multiplies the final result. Let's apply this to the example from the textbook. Find the derivative of f of t equals 2t to the fifth. Here, our constant a is 2, and our variable part is t to the fifth. First, we differentiate t to the fifth using the power rule. That gives us 5t to the fourth. Now we just multiply this by the constant, 2. So the derivative f prime of t is 2 times 5t to the fourth, which equals 10t to the fourth. You see, the 2 just multiplied the result. A crucial skill in differentiation is recognizing when a function needs to be rewritten before you can apply the rules. The power rule, f of x equals ax to the n, is our main tool for now. So if a function isn't in this format, we have to use algebra to get it there. This often involves using the laws of indices. Remember, for instance, that 1 over x to the n is the same as x to the power of negative n. Let's look at worked example 9.11. Differentiate y equals 6 over x squared. As it's written, this is a quotient, and we don't have a rule for that yet. But we can rewrite it. Using our laws of indices, we can rewrite x squared in the denominator as x to the power of negative 2 in the numerator. So y is the same as 6x to the negative 2. Now, this looks familiar. It's in the form ax to the n, where a is 6 and n is negative 2. Now we can apply our rules. The derivative, y prime, will be the constant 6 times the derivative of x to the negative 2. That's minus 2 times x to the power of minus 2 minus 1. Simplifying this gives us negative 12x to the negative 3. And if we want to write the answer without negative exponents, we can express it as a fraction. This is equal to negative 12 over x cubed. So the key was to first rewrite the function into a form we could work with. So far, we've only handled functions with a single term. What happens when we have a polynomial with multiple terms added or subtracted? The good news is, it's incredibly simple. This is governed by the sum and difference rule. The rule says that the derivative of a sum or difference of terms is just the sum or difference of their individual derivatives. This means we can just differentiate our function piece by piece, term by term. It's a divide and conquer strategy. You just handle each term on its own and then put them back together. Let's see this with worked example 9.12. Find the derivative of y equals 7x minus 2. We'll differentiate each term separately. Let's start with 7x. Remember that 7x is the same as 7x to the power of 1. Applying our rule, the derivative is 7 times 1 times x to the power of 1 minus 1. That's 7x to the power of 0. Since anything to the power of 0 is 1, the derivative is just 7. Now for the second term, negative 2. What's the derivative of a constant? We can think of minus 2 as minus 2 times x to the power of 0. When we bring the power, 0, to the front, the whole expression becomes 0. So the derivative of any constant is always 0. This makes sense, as a constant function like y equals minus 2 is a horizontal line, and its gradient is always 0. Now we combine our results. The derivative of 7x is 7, and the derivative of minus 2 is 0. So dy by dx is 7 minus 0, which is simply 7. Now a very important point. We do not yet have rules for differentiating a product or a quotient directly. You cannot just differentiate the parts of a product and multiply them. And you can't differentiate the top and bottom of a fraction separately. So for now, our strategy must be to use algebra first. If you see a product, expand the brackets. If you see a quotient, divide through to get a sum of individual terms. Let's try this with a product. Find the rate of change, which is just another way of asking for the derivative of y equals the quantity x plus 3 times the quantity x minus a. First, we must expand the brackets to get a sum of terms. Using FOIL, we get x squared minus ax plus 3x minus 3a. We can group the middle terms to get x squared plus 3 minus a times x minus 3a. Now it's a polynomial, and we can differentiate it term by term. The derivative of x squared is 2x. The derivative of 3ax is just the constant coefficient, which is 3 minus a. And the derivative of the constant term minus 3a is 0. So the derivative is 2x plus 3 minus a. Let's do the same for a quotient. Let's differentiate f of x equals x squared minus 6 all divided by 2x. Again, we must rewrite this first. We can split the fraction by dividing each term in the numerator by the denominator. This gives us x squared over 2x minus 6 over 2x. Simplifying each term, we get 1/2 x minus 3x to the power of negative 1. Now we can differentiate this term by term. The derivative of 1/2 x is just 1/2. For the second term, we have minus 3, and the derivative of x to the negative 1 is negative 1 times x to the negative 2. The two negatives make a positive, so we get 1/2 plus 3x to the negative 2. Let's now circle back to our second learning objective, using the derivative to analyze a function's behavior. Remember, the sign of the derivative tells us whether the function is going up or down. Specifically, if the derivative is positive on an interval, the original function is increasing on that interval. If the derivative is negative, the function is decreasing. We can use this to solve problems algebraically. Let's find the interval where the function f of x equals 5x squared minus 12x plus 3 is decreasing. The question is about decreasing, which is a question about the gradient. So our first step is always to find the derivative. Differentiating term by term, the derivative of 5x squared is 10x, the derivative of minus 12x is minus 12, and the derivative of 3 is 0. So f prime of x is 10x minus 12. We want to know where the function is decreasing. This happens when the gradient is negative. So we need to solve the inequality f prime of x is less than 0. That means we need to solve 10x minus 12 is less than 0. This is a simple linear inequality. We add 12 to both sides to get 10, x is less than 12. Then we divide by 10 to get x is less than 1.2. So our function is decreasing for all values of x less than 1.2. To finish, let's look at a common source of errors by putting ourselves in the shoes of an examiner. Here's a problem. Differentiate y equals the quantity 6x squared minus 5x all over x cubed. Let's analyze a few incorrect attempts. Solution 1 gives the answer as 12x minus 5 over 3x squared. This student has differentiated the numerator and the denominator separately and then put them back in a fraction. This is incorrect. There is no such rule for differentiating quotients. This is perhaps the most common mistake students make when they start learning differentiation. You cannot differentiate the top and bottom of a fraction independently. Solution 3 tries a different, but also incorrect, approach. The student rewrites the function as a product and then differentiates each part of the product and multiplies the results. This is also wrong. While there is a product rule, which we will learn later, this is not it. So what is the correct method? The correct method, as we've practiced, is to simplify the expression first. We split the fraction to get 6x to the negative 1 minus 5x to the negative 2. Now, we differentiate this simplified form term by term. The derivative is negative 6x to the negative 2 plus 10x to the negative 3. This is the correct process and the right answer. Alright, let's recap what we've accomplished today. We have moved from a graphical understanding of the derivative to a powerful algebraic one. We learned the fundamental rules for differentiation, the power rule, the constant multiple rule, and the sum and difference rule. These tools allow us to differentiate any polynomial. Crucially, we also established a key strategy. When faced with products or quotients, we must first use algebra to rewrite the function as a sum of terms in the form ax to the n. Finally, we apply these skills to determine where a function is increasing or decreasing by analyzing the sign of its derivative. We have successfully met both of our learning objectives. The key to mastering this is practice. I strongly encourage you to work through the exercises in the textbook. Start with the basic problems and build your way up to the more complex applications. Thank you, and I'll see you next time.